Okay, our next topic in our deep reinforcement learning course is trust region-based methods for reinforcement learning. This is a slight step away. It relates to policy gradient approaches. However, we'll see, let's say, a different type of optimization approach that relates to policy gradient. I'll explain it during this lecture. So in general, we are still discussing policy gradient methods, a variant of the policy gradient method. And we're going to use function approximators. And we're using a type of factor critique framework. We'll use an advantage function in some cases, along with the policy approximator. And of course, this all relates to deep reinforcement learning. I think it was actually originally presented using deep neural networks. So it also relates to deep RL, or considered deep reinforcement. Okay, so let's first of all, let's try to define reinforcement learning as an optimization problem with an objective function and maybe some constraints, but a classic optimization problem. This will be more in line with classical machine learning, or classical with supervised machine learning, where we usually define the machine learning objective as a reduction to some numerical optimization problem. Right, so in supervised learning, we usually try to minimize some training error, some loss function, right, that is defined over our training error. In reinforcement learning, though, we usually try to use observations from the environment, some interactions, in order to compute the optimal policy. Right, so let's try to define that objective and the constraints affiliated with that. So first of all, we saw an approach that resembles this optimization approach, general optimization approach, right, for Q-learning. Q-learning can in principle consider all transitions seen so far, however, and we've seen this before, right? Do you remember which method we saw where we take into account all of the interactions in order to learn the best, in a closed form way, we computed the best Q values, given all of our observations, or those that minimize some loss, some TD loss specifically. We saw one such method during this course.
Something before DQN? Something before
DQN, yeah. Specifically with a linear approximator.
Yes.
Right, so the least squared method, right?
Yes, yes.
LSTD, least square temporal difference method, that allowed us to iterate or to consider all of the interaction, the transitions that we've seen so far, and compute the Q values which minimize the one-step temporal difference error over the entire data set in a closed form way. It was, if you remember, it was, well, you don't remember, but it was more computationally intensive, and it required a linear approximate. But in many cases, it's still actually a very powerful tool. We discussed it previously. You should go back to the previous lectures. Okay. Next, we also discussed policy gradient methods. So, by the way, if we can do such optimization for learning Q values. However, these are optimized some, let's say, proxy objectives of if our objective is indeed to learn the optimal policy. Learning Q values can imply the optimal policy, but we're not directly learning the optimal policy, right? We're learning something else that can translate to an optimal policy. Policy gradient methods do optimize the policy, but are not sample efficient, right? They do on-policy learning. We would like to formalize a gradient update step as an optimization over all previous samples, where the input is a data sampled from some policy, and the output should be a new policy which maximizes the expected return. So again, looking back at vanilla, the basic policy gradient method that we've seen before, the reinforce algorithm, or even the simple the A to C algorithm, In these, we have some limitations where, first of all, it might be hard to choose the correct step size. Not only that it's hard, it's also risky. If you choose the wrong step size, you might be in trouble here. Because the input data is not input data which is just transitions from the environment, right? It is non-stationary due to changes in the policy, right? The policy evolved, and so the data that we observe is non-stationary. That is, the state and reward distributions are non-stationary. They change with the policy. And in these cases, if we take a bad step size, that can be very catastrophic. Much more so than in supervised learning, where in supervised learning you can usually recover from that. In reinforcement learning, you might not be able to recover. You might observe what's called a performance collapse, right? How can that happen? So here we have a very simple policy here on the left, which is defined only with a single tunable parameter, let's say theta n. That's the only one that we're updating now. And now we computed the gradient in the performance in J with respect to our tunable parameter. And the gradient told us, well, this is the direction of improvement. What will happen if we take too big of a step? Well, we might end up in this value of theta n. Once you reach this area of theta n, you have a lot of gradients here in different locations, right? But you'll probably get stuck in a very bad behavior, and gradients won't be very informative because they relate to a very noisy region of bad behavior. Okay, so indeed this might happen, and it does happen in many cases, where we take too far of a step, we reach a bad policy, the next batch is collected under the bad policy, and our RL agent is not able to recover, and we see a collapse in performance. You might, by the way, you're more than welcome to try this in your home assignments, right? You are implementing several deep RL algorithms. Try setting the learning rate too high and see what happens. In many cases, you'll actually see that it learns to a certain point, and then you'll see a collapse in performance. So this is a real issue. Another limitation of vanilla policy gradient methods is that they only consider one gradient update per environment sample, if you remember the A2C algorithm that we've seen before. We would like to better utilize previous experience. Another issue that in vanilla policy gradient is that it depended on scaling of coordinates. That is, the issue is that it uses the same learning rate for all states and all tunable parameters, which might be problematic in high-dimensional optimization problems. Although we saw one optimization method that can adapt the learning rate per dimension, it can help in these cases, which was?
Eligibility traces?
So our TA will get, you'll have to retake the course. No, we saw the ADAM optimizer, the adaptive optimizer. Okay. That can help in this case. Okay, so far we saw the policy gradient algorithm. This is also known as a line search method. Right, we just do gradient ascent or descent, but with a simple linear gradient approximation. We find the direction of improvement, of most improvement. I mean, again, it's just the direction of improvement for if we have a single dimension, but in many dimensions, the gradient actually points at the direction of most improvement. Then we select step length and we do that update. Today, we're going to look at a slightly different approach that is based on trust region principles. So what we're going to do today is we're going to select a trust region around our current policy, and we'll define a trust radius, how far we are willing to consider away from our current policy. This will be analogous to a maximum step length in the regular policy gradient method. And then we're going to compute directly the optimal point within that trust region. Okay, so we're going to have constraint optimization. Do you remember what tools, mathematical tools, are usually used to solve constraint optimization in continuous spaces?
Mathematical tools.
An Italian guy, then went to France. Lagrange. Okay,
Lagrange optimization.
Right, Lagrange. Okay. So you can think of the difference using this example here, where you're trying to get to the top of the hill. Where's my pen? There we are. You're trying to get to the top of the hill, right? You're standing right here. And you're assessing very locally, the gradient is assessed very locally, what is the direction of most improvement, of most, the steepest incline, right? And let's say that it's this yellow line. I need how to point, okay. Let's say it's the yellow line. And you can see what happens if you take too big of a step, right? You'll fall off the cliff just because it is locally the direction of steepest incline. But once you go beyond the very local region, that's not the case. You can fall off the cliff. And as we said before, that happens many times in reinforcement learning. So instead, we're going to define a trust region. You see the yellow ball here around our current policy, our current point. And we would like to compute the best policy within this region, right? The one that the policy that returns the highest expected return within this bounded region. And, well, we'll just take the step towards the direction. And you can see that within the trusted region, we'll hopefully have a more stable climbing to the top of the mountain, right? In a more stable way. And indeed, I mean, I'll show you later that under some assumption, this is indeed what we get. Okay, so the general idea would be as follows. By the way, any trust region method, these go beyond reinforcement learning. We start by approximating an objective function, our true objective function, that can be j, for instance, right? The expected sum of return. With a simpler function, let's call it f tilde. And then we solve the argmin or argmax, depending if we're doing j. If we're doing rewards, we'll do the argmax. If we're doing costs in other type of control problems, then we'll find the min of the function. We'll find the minimum or the optimum of our approximated function. And that will be our solution to the true function. Okay, to the real function. What's the problem here? The problem is that of course the solution for the approximated function might be wrong. Why might it be wrong? Because you find the optimum for the approximation function, for your approximated function f tilde. But it might be the case that for that region, for that optimum point that you find, that might be you might have a very bad approximation at that point, right? It might be very far from the true objective function. So your approximated optimal solution might be very far from the true optimal solution. So the solution that we're going to observe today, to explore today, would be to restrict the search to the region where we trust our approximated function to approximate the true function decently well. That is, we're going to solve the argmin or argmax, we'll find the optimum point of f tilde x, but as long as x is within some trusted region, some area in our approximation that we trust.